What's up, everyone? Hope you're doing well. And today we're going to be starting chapter 4 in our textbook, which is a chapter on matrices. Okay. In section 1, we're going to be looking at what a matrix is. And then I'm also going to cover section 2 in this video, where we're performing different operations on matrices. Okay. So understand matrices is just the plural of the word matrix. Okay. Matrix is singular, matrices are plural. All right. So, what is a matrix? It's simply an array or an arrangement of numbers. Okay. And you can see we have matrix A on our screen here. It's matrices are often represented in mathematics with a capital letter. Okay. And this particular matrix has 3 columns to it and 2 rows. Okay. So you can see that the columns are in a vertical direction. So the first column has the elements 2, 0. The second column has the elements 3, 4. The third column has the elements -1 and 3. And then your rows are horizontal. The first row has elements 2, 3, and -1. The second row has elements 0, 4, and 3. And notice we've simply just put brackets around that entire arrangement of numbers. So typically a matrix has brackets around it. Okay. Now every matrix has a dimension to it, or an order, and that's simply the number of rows by the number of columns. The number of rows by the number of columns. So for matrix A here, we would say its dimensions, or its order, is 2 by 3. It has 2 rows and 3 columns. Okay. And notice we're using an X there in between the 2 and the 3, kind of like to represent multiplication. So like if you were to multiply 2 and 3 together, that gives you 6. And notice we have 6 total numbers or elements that make up the matrix. Okay, so the dimensions will tell you how many elements are in the entire matrix. Okay. Once again, a matrix element, it's a specific number within the matrix, and we have a notation to represent each of those elements. So if we're working with matrix A, where it's represented with a capital letter, then using a lowercase a would be referring to a particular element within the matrix, okay? And then notice here we have the lowercase a followed by a subscript of 1, 3. So that means we're looking for the element in matrix A that's in the first row, third column. First row, third column. And that would be this guy right here, -1. Okay. So there's a lot that I just threw at you there in that this one screen here. I want you to click over to practice 1. You're going to be given some different matrices and asked about the dimensions of each of those matrices, as well as finding a particular element of each matrix. Okay, so pause the video, work through those, and then check your work with mine. All right, moving forward. It is possible to set 2 matrices equal to one another, okay? When the 2 matrices are equal, they have to have the same dimensions though, and that means their corresponding elements have to be equal to each other. So what I mean by that is whatever numbers in the first row, first column of the first matrix has to be equivalent to whatever numbers in the first row, first column of the second matrix, okay? This can lead us to matrix equations. So here's an example of one. Both of these matrices are 2 by 2 matrices. 2 by 2, 2 rows, 2 columns. And those are called square matrices when your rows and your columns are equivalent to each other. Okay. So I would like to solve for each variable that is showing up within this matrix equation. Okay. So notice the first variable is x, and that's within the first row, first column element of the first matrix there. I can solve for x by simply setting it equal to 3, which is the first row, first column element of the second matrix. And that means x is going to equal -1. Okay. If I want to solve for y, that's in the second row, first column of the first matrix. I would set it equal to its corresponding element from the second matrix, which is 12. Solving there, I end up with y equals 9. And similarly, if I want to solve for z, I'm going to set 2 equal to 2z minus 4, since those are corresponding elements. And that's going to solve to z equaling 3. Okay, so pretty simple. All right, moving forward, here's another matrix equation. Okay, the two matrices that have been set equal to each other are both 2 by 1 matrices, 2 rows, 1 column. I know the second matrix, it almost appears like it's a 2 by 2, but what you have to understand is that this 3x minus 2, it represents one element of the matrix. It's the first row, first column element. And then same thing down here. This is the first row, first column element of the second matrix, okay? So with the two matrices being equal to each other, set their corresponding elements equal to each other. And what this particular equation leads me to is a system. Okay, this is a system of equations now. And I can solve this very easily with substitution. It's set up perfectly to take 3x minus 2, substitute it in right there. So let me show that over on the right. That'll lead me to 3 equals 2 times the quantity of 3x minus 2 plus x, or 3 is equal to 6x minus 4 plus x. 7 is equal to 7x. That means x equals 1. Okay, so there's the value of x. And then to get my value for y, I will simply plug in 1 for x into the top equation there. And that's going to give me 1 as well. Okay. Now you can write this as an ordered pair. You can say the solution is 1 comma 1, but it's not necessary here. Okay. All right, moving on. Now we're looking at some different operations on matrices. Okay, so you can see in this example, I have two matrices. They are both 3 by 3 matrices. Both matrix A and matrix B have 3 rows and 3 columns. All right. So first thing I want to do is add the two matrices together. Okay, add A with B. Very simple to do. To add matrices together, they have to have the same dimensions, which these two do, and you're just going to add their corresponding elements together. Okay, so that's going to lead me to the following. I'm going to get another 3 by 3 matrix out. The first row, first column element would simply be 3. All you'd be doing is adding 1 with 2. Okay. Then we'd, in that next position, so that would be first row, second column, you'd get 7, and then -4. Okay. And then I think you kind of get the idea. Now I move to the second row elements. -4 plus 5 is 1. 5 plus 0 is 5. 0 plus -2 is -2. And then add the elements in the third column together. -6, -9, and 13. Okay. All right. In the middle problem here, I'm asked to find 3a. This 3 is known as a scalar. Okay. And all this really wants me to do is take each element of matrix A and multiply it by 3. Okay, so that's going to lead me to 3, 9, negative 15 for my first row, then negative 12, 15, 0 for my second row, 12, negative 24, and 27 for my third row. Okay. All right, and then you can see in the last problem here, we're asked to find a combination of 3a subtracted by b. Okay. You would want to follow our order of operations here, just like you're working with any other numerical expression. Okay, so that means do the multiplication first, find 3a, which we've already done. That's the matrix that's in red. And then you'll take the elements from matrix of 3a and subtract them by the corresponding elements of matrix B. Okay, so that's going to lead me to the following: 1, 5, and negative 16 for the first row. So for example, to get that 1, I just simply took 3 subtracted by 2 from matrix B. Okay. To get the 5, I did 9 subtracted by 4. And then to get the negative 16, I did negative 15 subtracted by 1. Okay. So then follow the same process for the second and third rows. You'll end up with negative 16 or negative 17, 15, 2, 22, negative 23, and positive 23. Okay. All right. So notice in those examples we covered matrix addition, matrix subtraction, and then scalar multiplication. Okay. So those are the three operations we've looked at so far. And that's going to lead us to some properties of matrix operations. Okay, so for any matrices A, B, and C whose dimensions are the same, and any scalar C, so notice I'm using a lowercase letter c here, that means the following hold true. The commutative property of addition that works for real numbers, well, it also works for matrices. Matrix A added with matrix B would be no different than matrix B added with matrix A. Same with the associative property of addition. Matrix A added with the sum of matrix B and C would be no different than the sum of matrix A and B added with matrix C. And then distributive property is going to hold true for scalar multiplication. So if I'm taking a scalar C and I'm multiplying that by the sum of matrix A and B, that would be no different than the scalar of C multiplied by A added with the scalar of C multiplied by B. Okay. All right, so just bringing your attention to some different properties associated with our matrices.